Good evening, all. I welcome you all in the week 6 weekly assignment practice and live interactive session on the course code NOC23-CY38 Introduction to Chemical Thermodynamics and Kinetics. Myself, Harpriya Minhas from Department of Chemistry, IIT Indore. So let's wait for a couple of minutes so that others could join the class. Okay, let's start today's session. Okay, before jumping into the question session, like assignment questions, let's revise what we have done during this week. So we studied about the phase equilibrium, what is phase transition, transition temperature and all. So this phase is a substance is a substance form of matter that is uniform throughout the chemical composition and the physical state. That is what you call a phase. And the phase transition, so phase transition, when your system is converting from one phase to another phase, that is called phase transition. So that is a spontaneous conversion of one phase into another phase, occurs at a characteristic temperature for a given pressure. So for example, you can take the example of water, from where your ice is converting into liquid, or your liquid is converting into vapor. So your transition temperature, so at the temperature where your transition is taking place, that is known as transition temperature. So at that temperature, your Gibbs free energy is minimized, and that is delta G is equals to 0. And next we discussed about some terms like triple point, critical point. So at triple point, where your solid, liquid and vapor, like here your solid, liquid and vapor, all the three states are present. So this is known as triple point. So this critical point is the temperature after which your vapor and this is going to behave as a superfluid. Okay, so the general region of a pressure and the temperature where solid, liquid and gas is stable, so that has a minimum molar Gibbs free energy, known as shown in this phase diagram. Okay, for example, a solid phase in the most stable phases is at low temperature and the high pressure. So this is what we know, right? At low pressure and low pressure and low temperature, this is at low temperature, and this solid is forming at high pressure, right? So at this condition, your solid state is forming, and you can relate with your vapor. Your temperature is increasing and your pressure is low, right? And as your pressure is increasing and temperature is increasing, you are converting into liquid state. At normal temperature and pressure, the molar Gibbs free energy of a graphite is lower than your diamond, but still your diamond phase exists, right? So you can correlate. So however, for the transition to take place, the carbon atoms must change their locations, which is immediately slower process in a solid except at a higher temperature. So this is well discussed in the class, right? So thermodynamically unstable phases that persist because of transition is kinetically hindered are called metastable phases. So here diamond is a metastable phase, right? So diamond is a metastable phase of a carbon under a normal condition. So we can get the diamond, but still at the normal condition your graphite is stable, but still we call as a diamond as a metastable phase. So next are phase diagrams. So these diagrams, these are between the pressure and temperature, right? The pressure versus temperature graphs. It shows the region of pressure and temperature at which its various phases are thermodynamically stable. The lines separating the regions are called phase boundaries, right? And then the conditions of free vaporization throughout the liquid are called boiling. And the boiling temperature. The temperature at which the vapor pressure of a liquid is equal to the external pressure is called boiling temperature. At that pressure, for the special cases, the external pressure of 1 atmosphere, the boiling temperature is called normal boiling point. With the replacement of 1 atmosphere by 1 bar as a standard pressure, there are some advantages in the use of standard boiling point. So these are basic terminologies that you have known, right? Similarly, you can correlate with the melting point. So similarly, same terminology will go for the melting point also. Okay, this is a phase diagram of carbon dioxide, is CO2. So here you can see your critical point is at temperature 304.2, and your triple point is at 216.8, that is denoted by T3, and your boiling point is at 194.7 at 1 bar, right? So correspondingly, your T3, you can check your pressure, that is 5.11 atmosphere, and similarly you can go by your other corresponding values, like TC you are having 72. So here the important point is you are having a positive slope of solid liquid boundary. So you have a solid liquid boundary, this one. So this curve, this line is positive, this slope is positive, which indicates that the melting temperature of a solid CO2 raises as the pressure increases, right? So melting temperature, right? So this is a general trend that we know, right? And the other thing that you studied about this is that at the pressure 67, right, 67 atmosphere. So when you are putting your CO2 in, filling your CO2 in a cylinder, then you are keeping your atmosphere 67, so that you are filling it into a liquid form, so that it could be more dense and your quantity should be more when you are carried, right? But when you are opening it up, opening the nozzle of this 67 atmosphere to the one against the 1 atmosphere, then you can see the sparkling of solid form of the CO2 is coming out, that is known as dry ice, right? So this is because of sudden pressure change from 67 atmosphere to 67 atmosphere to 1 atmosphere. So due to the drastic pressure change, your liquid is directly converting into solid. So that is also known as cooling effect, defined by Joule-Thomson effect. So we know the temperature increases, pressure increases, then you have dP upon dt at constant volume. So changes from one phase to another phase. In a molar volume, you can define like Vm is greater, Vm of liquid is greater than Vm of solid. This is a general thing that you know. So your volume of liquid is higher than your solid, right? So this is why your slope of solid liquid curve is positive. Okay. So at the normal temperature and pressure from is the most stable that is the most stable phase at a constant pressure, that is 1 atmosphere that we are defining. So when we are cooling it immediately, so then it will be converting it into a dry ice that we just discussed. So now to get into the liquid, we need to increase the pressure. So we can reach to the liquid region when we are compressing by applying the pressure into it, right? So that so at a higher pressure, right? So next thing we know about the triple point. So triple point for CO2 511 atmosphere, this is what we defined at 21.6 Kelvin temperature, and critical point at 72.9 atmosphere. So correspondingly we can check the temperature. So next move into the phase diagram of water. Here is your vapor, liquid, and you are having a various solid states. Okay. So here water is having one liquid phase but many different solid phases other than the other than the ordinary ice that we usually have in our homes. So some of these phases melt at high temperatures, right? You can see this at higher temperature you are having these 7, 11. So these phases do exist at a higher temperature. And for instance, melts at 100 degrees Celsius but exist only above 25 Pascal, 25 kilopar. So note that the 5 more triple points occur in the diagram. So here in the phase diagram of water, so you can see the 5 triple points that will be between solid state 1, 2 or different, or liquid or vapor or solid, so depending upon the adjacent phases. So each one occurs at a definite pressure and temperature that cannot be changed. The solid phase of a ice differ in arrangement of water molecules under the influence of very high pressure. Hydrogen bonds buckle and the water molecules adopt different arrangements. So these water molecules, so in solid, you know about the tetrahedral geometry of this, right? So these solids can arrange into different arrangements, different molecular arrangements, so that they are differing from one another. So these polymorphs or different solid phases of ice may be responsible for the advance of glaciers. So this is what we discussed, right? So the glacier ice is different than your normal ice. So here we can see that on increasing the temperature, you are deviating from your original structure, from the tetrahedral geometry. So your structure is collapsing as you are increasing the temperature. So second important point is your solid liquid curve that we have seen in the carbon dioxide phase diagram, that is positive, but here that is negative. So especially this curve is negative. So this is having negative slope. Okay, so that is your ice, when you're converting your ice to water near 0 degree Celsius. So decrease in the molar volume, and that decreases the slope of the curve near the phase diagrams to be negative. Right, so this is well explained in the lecture. So next is phase diagram of helium. So here we are covering the two isotopes, the helium-2 and helium-1. So here helium-1 is following the normal trend, but the helium-2 is behaving little different due to the superfluid. So now you can check the triple point, where the triple point, your boiling point and your critical point against the temperature and pressure are existing. So here the phase diagram for helium, here we provided for helium-2 and helium-1. So the lambda line marks the condition under which the two liquid phases are in equilibrium. So this is your lambda line, so which is providing when your two liquid phases are in equilibrium. So helium-2 is a superfluid phase, this one. So the superfluid phase, so pressure over the 20 bar must be exerted before the solid helium can be obtained. So 20 bar, you can see the 20 bar here maybe. So here 20 bar must be exerted before the solid helium, this one, sorry, can be obtained. So that will be in a BCC or HCP. So these label are HCP or BCC, so denoting in a different solid states. So their packing arrangement is different. So this HCP is a hexagonal closed packing and BCC is a body centered cubic, right? So their arrangement, atomic arrangements are different. So when considering the helium at a low temperature means here low temperature, it is necessary to distinguish between the isotopes 3He and 4He, right? So pure helium-4 has two liquid phases. The phase marked with helium-1 is in a diagram. This is a normal fluid, as discussed. This is a normal fluid, and other than that the helium-2 is a superfluid. This is because of its it flows without viscosity, so there is no against force in the flowing the helium, right? So what next we studied? So next we studied about thermodynamics of phase transition. So generally we go with the Gibbs free energy, but here we talk about the chemical potential. So that is defined by molar Gibbs free energy, right? So in total, when we define your delta G, so that is your number of moles that are going from one phase to another. So suppose it's moving from one to another, so this end is losing your number of moles, so this end is gaining your number of moles, right? So one end is at receiving and another end is at losing. So we can define by losing end by providing the negative sign. Suppose that is a phase 1, dn, that is change in the number of moles, and then other end is so your another end is gaining. So this end is your gaining and your change. So that will be, this is how you can provide the change. So at equilibrium you can see that your del G is 0. So next is effect of pressure. So we know the journal term that we derived from Maxwell equations. So this was the equation, that is del G equals to minus S dt plus V dp, and through here we got del G upon del T at constant pressure is equals to minus S, that is entropy. So but if we are defining in terms of chemical potential, that is del mu upon del T at constant pressure, that we can write it in the form of del G upon N upon del T at constant pressure. So this we can take it out and we can donate this as a minus S, right? So minus Sn, so that will be a molar entropy. So another is your nature of curves. So that you know about your pressure and temperature. So where you can see this is your gas, liquid and solid. So this is between pressure and temperature, but you can plot it between mu and temperature. So that is this is what you know. Your sudden change in the line will provide you the change in the phase. So this will be solid phase, liquid phase and vapor. So next I am just writing out down the formulas that some of them we are using in today's assignment questions. So first is effect of pressure for the liquid gas equation. So that is RT ln P upon P star is equals to Vm liquid del P. So that we are reporting as P is equals to P star in exponential form Vm L del P upon RT. So here your vapor pressure is increasing exponentially. So next that we have studied is the thermodynamics of phase transition, and here in phase boundaries we developed the equation of del P upon del T is equals to change in, so is transition from Sm molar upon del transition Vm. So this equation we state as Clapeyron equation. So on this basis we can plot the graph. So suppose your dP upon dt, this fusion Sm upon Vm, we can also write it in terms of V fusion Hm enthalpy upon T fusion Vm. So we split it split it up this entropy in terms of enthalpy and temperature. So suppose we are having pressure and temperature and your curve is moving like this. So here we are having solid and liquid. So here, so this is example of CO2, right? So here we are getting a positive slope. But when we are plotting pressure versus temperature and we are having a curve like this here solid and liquid, so this is an example of water. So here we are getting a, so here you can get a negative slope. So that means your F fusion V molar is less than 0. So here your delta fusion Vm is greater than 0. So that makes your slope positive in case of CO2 and negative in case of your water. Further driving the equation, we got pressure equals to P star plus delta fusion Hm upon T delta fusion Vm into change in temperature T minus T star. So this is between when the system is between solid and liquid equilibria. Similarly, we can define the equation for liquid and gas, that is liquid and vapor equilibrium. Liquid and vapor equilibrium. So that we can denote as P is equals to P star, that is in the exponential form, e to the power minus del vapor Hm upon R 1 upon T minus 1 upon T star. So this equation we can use when there is equilibrium between liquid and vapor, and this equation we can use when there is equilibrium between solid and liquid. And these equations these equations are known as Clausius-Clapeyron equation. So next we know about NFES classification, where we say your alpha phase in equilibrium with beta phase, and we can donate the equations in terms of mu, that is del mu beta upon del p at constant temperature minus del mu alpha upon del pressure del p at constant temperature is equals to Vm beta minus Vm alpha. So similarly we can denote in terms of entropy. That is minus Sm beta minus plus Sm alpha. So next we studied about the phase transitions, that is first order phase transition. and your second order phase transition. So here in first order phase transition, your slope is discontinuous at the transition, but in second order your first derivative is continuous but your second derivative is discontinuous. At the transition, and you have gone through multiple examples of this first order phase transition and second order phase transitions, and the phase transition which doesn't follow your first order, either your second order, so that is a different third phase transition that also you have studied. Okay, let's move to the question session, and at the end of this session, if we are having some time, then we can discuss about the degree of freedom and the components and the phases, right? So for now, let's move to the questions. Here is the first question. The vapor pressure of dichloromethane at 20 degrees Celsius is 58 kilopascal, and its enthalpy of vaporization is 32.7 kilojoule per mole. Estimate the temperature at which its vapor pressure is 66 kilopascal. So here ultimately you have to find the temperature at which your vapor pressure is 66. So this is your T, how you have to find. T star, you know, like you have given the T star, that is 20 degrees Celsius. So in terms of Kelvin, that will be 293. And next is del vapor H. This enthalpy of vaporization we have 32.7 kilojoule per mole. Next we have given the P star. P star is 58 kilopascal and P is 66 kilopascal. So here we can use the formula ln P star upon P is equals to del vapor H upon R 1 upon T minus 1 upon T star. So from here we can take out this to the left side and put all these values in the equation. We can get the T star. So R, we know here all the values are in joules and pascal, so we can use the value of R. So here R is 3.14 joule per Kelvin per mole. So now let's put these values in the equation. So now I am taking this 1 upon T into the left side. So that will be 1 upon T equals to 1 upon T star plus R right. So this is the equation that we'll get. Now putting the values here, so T star is 293 plus R will be 8.314 joule per Kelvin per mole. So your del vapor H is 32.7, so that is kilojoule. So we are converting into joule, 10 to the power 3 joule per mole into ln P star upon P. So this will be P, right? Yeah. So your P star is 58 upon 66. So what will be the value of 1 upon T? So are you getting 1 upon T is equals to 3.378 into 10 to the power minus 3 per Kelvin, right? Okay Gopika, okay, fine. So what will be the value of temperature? In reciprocal, what will be the value?
295.85.
295.8. Okay, so can we write it into 296?
Yes, ma'am.
Yeah, so that is Kelvin. So what will be the value in Kelvin? So we got the value in Kelvin. So what will be the value in degrees Celsius? Yeah, 23 degrees Celsius, right? So now go back to your options. So now you are having 23, that is your option A, right? Okay. So moving to the next question. So it states that the molar volume of a certain solid is 142 centimeter cube per mole at 1 atmosphere and 427.15 Kelvin its melting temperature. So the molar volume of a liquid at the temperature and the pressure is 152.6 centimeter cube per mole at 1.2 megapascal. The melting point changes to 429.26 Kelvin. Calculate the entropy and enthalpy of fusion. So here you have to find your delta S and fusion enthalpy H of a solid. So here you are given your molar volume, (142 centimeter per mole) at temperature 427.15 Kelvin and pressure 1 atm. So this is your solid. So your liquid is 152.6 centimeter cube per mole at temperature 1. So from here we can find your del V, right? So del V fusion is equals to Vm liquid minus Vm solid. So now 152.6 minus 142.0 centimeter cube per mole. So that will be your change in volume, del fusion V. Similarly, we know the pressure. So this pressure we are having 1.2 megapascal. So this 1.2 we can write 1.2 into 10 to the power 6 Pascal, right? And your temperature is 429. Okay, so now we know dP upon dt is equals to del fusion S upon del fusion V. So from here del fusion S is equals to your del fusion V dP upon dt. I'm just taking this volume term into your to your left side. So this will be del fusion V, and in terms of delta, this del I'm using your delta, that is dp del p upon del t, so that we can subtract your initial and your final pressure and temperature. Okay, so now this volume we have just subtracted here. Let me put it here. 152.6 minus 142, so that will be in centimeter cube per mole multiplied by your change in pressure. So change in pressure is 1.2 megapascal, right? Megapascal into 6 minus, so other is your 1 atmosphere. So 1 atmosphere, you know, it's 10 to the power 5 Pascal, right? So that will be 1 into 10 to the power 5 Pascal upon your change in temperature. So that is 429.26 429.26 minus 427.15 in Kelvin, right? So what you will get? So all units you are having a like standard unit, but here you are having a centimeter. So you have to convert the centimeter into your meters, and then you can go ahead to find your del fusion S. So this will be after subtracting what value you will get. Here you will get 10.6, right? Centimeter cube per mole into, so now I'm converting into meter. So 1 meter cube, so that will be your 10 to the power 6. So 1 meter equals to 100 centimeters. So accordingly I'm converting 10 to the power 6 centimeter cube into. So what you will get after solving this? So what is the answer after solving this equation? This one. So are you solving this? So that will be 12 minus 1 into 10 to the power 5 upon how much? Divided by 2, approx 2. So I think you will get around 5.21 into 10 to the power 5 Pascal into per Kelvin, right? Now solve it all. You will get, so this 5, this 10 will cancel out, this centimeter, yeah. So ultimately you will get 5.52 Pascal. Yeah, right Gopika, yeah. It's 5.52 I'm considering, okay. Pascal meter cube per Kelvin per mole. So let's check this answer. For entropy, for your entropy, it's how much? 5.526, 5.52, 5.5, right? This C, right? 5.5, but this is in joule per Kelvin per mole. So you have to convert your Pascal into your joule. So what will be the unit? Like you're converting your Pascal into your joule. So after cancelling all, you will get 5.52 joule per Kelvin per mole. So that means this meter is going to cancel out, right? And now you have just calculated your del fusion S, but you have to find your del fusion H. So you can use the formula TF into del S. So this formula you know, right? So that is del S is equals to del H upon T. So this is what we are using here. So this temperature we know. So this temperature is this one, right? At this temperature 427.15 Kelvin into your value 5.52. How much? So what will be the value of your del fusion H equals to? Okay, how much? 2357. Okay, 2357, right? That will be in joule per mole. So now we can convert into kilojoule. That will be 2.357 kilojoule per mole, right? Now check your answer. So that is C, right? 5.5 and 2.4. So you can approximately write this is 2.4 kilojoule per mole. So that is option C. Okay, moving to next question. So here the vapor pressure of liquid between 15 degrees Celsius and 35 degrees Celsius fits the expansion log P equals to 8.75 minus 1625 upon temperature in Kelvin. Calculate first part, that enthalpy of vaporization and the normal boiling point of benzene. So here first you have to find del vapor H, enthalpy of vaporization A, and B you have to find your boiling point, that is TB, right? Okay, so your equation given is log P is equals to, so this is your constant, right? So I am writing it as a constant value minus, so this is how you can write it, del vapor H upon RT right into 2.303, that is your log change, right? So from here you can find your del VH. Oh, sorry. So this del vapor H, this one. Take this to left side and put all the values here. Therefore, del vapor H is equals to your R so this value you have. So I'm just taking out your this value. So this value is this, right? So I'm taking out this, I'm comparing your this value. So I'm comparing your this value with 1625. So before that you can also understand from so this is your equation, log P equals to 8.75 minus 1675. How much? 1625, sorry. 1625, that is per temperature Kelvin. Right, so here I'm saying your log P is equals to constant minus del vapor H upon RT 2.303. So that is due to your natural log, right? So I'm saying your this value is equals to this value. So I'm comparing your these two values here. I'm just considering your these two values and just relating your left side and right side, and from there I'm calculating your del vapor H. So here your 1625, right, Kelvin into 2.303. So what will be your answer? Kelvin you cancel out, and that will be in joule per mole. So what you will get after multiplication? So what we will get after multiplication? Okay, 31,114, right? So this is 31,114. Oh, that's okay, 10, right? So that will be in joule per mole. But your answers are in kilojoule, so you can convert it into kilojoule. That will be 31.114 kilojoule per mole. So that is B, right? But still we have to find the boiling point. Yeah. Okay. Now let's find out your TB. So now I'm considering your normal boiling point. So your normal boiling point corresponds to when your pressure is 1 atmosphere, that is 760 torr. So here we are having the pressure value in torr, so that's why we are considering 1 atmosphere is 160 torr. So here instead of pressure I'm putting your 760. Okay, 760 is equals to, so that is your constant is 8.75 minus your value 1625 upon K, T upon K. So now from here we are considering your boiling point TB. So we are considering your normal condition of your boiling point, right? When your system pressure, vapor pressure becomes equal to your external pressure, right? This is what we studied about the boiling point. So from here we are considering your external pressure is 1 atmosphere, so we are putting in terms of torr because your pressure given is in, this one is in torr. So I'm putting your pressure here, that is 760 here, and then I'm considering this is your B. Now this T will be convert into B, that is boiling temperature. So now rearranging these terms you will get your TB. So I'm taking your right side, 1625 T upon K is equals to, so I'm taking this here and this log term into this side, so that will be your 8.750 minus log your 760 torr, right? Now I have to find out this. Now I'm again rearranging your terms, 1625 upon 8.750 minus log 760. So can I rearrange in this way? Now solve this and let me know the answer. Okay, Gopika, you are getting 276.8. Okay, 276.8. Okay, so now see, this is your unitless quantity, right? But here your temperature, your TB per Kelvin. So now you take your per Kelvin to other side, you will get 276.8 Kelvin, right? So this is your boiling point of your benzene. Now going back to the options, you are having 276.8, 276.9, so that is prox, right? So your answer is option B. Right? So here is your next question. So it states when a certain liquid freezes at minus 3.65 degrees Celsius, its density changes from 0.789 gram per centimeter cube to 0.801 gram per centimeter cube. Its enthalpy of fusion is 8.68 kilojoule per mole. Estimate the freezing point of benzene at 100 megapascal. And your given is your molar mass of benzene 46.07 gram per mole. So again you have to find the temperature, that is, now you have to find the freezing point of benzene. So here your T final is, this is your minus, so that is minus 3.65 plus 273.15, right? So that will be your how much? 269.5 Kelvin. So here your change in density is given. So this is your density, rho 1, rho 2. So your enthalpy of fusion, that is delta H, 8.68 kilojoule per mole. So your freezing point at pressure, so this pressure is given, that is 100 megapascal, so that is 100 into 10 to the power 6 pascal, right? So now we are having the equation del P upon del T is equals to del fusion S upon del fusion volume V. Now I can rearrange this term like del T is equals to del fusion V upon del fusion S into your del P. Now I am expanding your entropy in terms of enthalpy, that is H upon T, right? So H upon T means H will come in the denominator and your temperature is going to multiply in your numerator, that is your TF. So TF del fusion volume upon del fusion H into your del P. So now I can state this term as TF del P, I'm taking it here, upon del fusion H. So now you know the relation between rho is equals to density is equals to mass upon volume, right? So I need a volume here, so I'm now changing your volume, I'm replacing your volume with your mass upon rho, right? So now this volume, the change in your volume, I can state it as your mass into your change in rho, right? 1 upon rho. So now accordingly we are putting our values, like from values from here in this equation to get your del T. So your TF is 269.5 Kelvin into your pressure. So your pressure is how much? 100 100 into 10 to the power 6 Pascal into your mass M. So I'm considering M till now. So your del fusion is how much? 8.68 kilojoule. 8.68 kilojoule per mole into your change in density. That is changing from here to here, 0.789 minus point how much? 0.801. So this is in your gram per centimeter. Now after solving, what you will get? So this is what you will get after solving this whole term into your mass into how much density you will get. So what you will get after solving this, or this term, So this is your centimeter cube, right? -3. So I think you will get 0.0 0.01899. So this is what you are getting. Okay. So I'm putting here your 0.01899 centimeter cube per gram. So now your things are in Pascal and Joule, and again you have to convert your centimeter into meter. So now I'm multiplying with, now you're converting into meter cube into 10 to the power 6 centimeter cube. So now what you will get? So what you will get? 5.88. So now multiply your mass 46.07 . So what you will get? Okay, I'm directly writing your answer. So you will get 2.17 Kelvin. So now ultimately you have to find TF. So that will be, so your initial temperature is 269. So this is what we got here, right? 269.5. 269.5. So this is, so this value, So this temperature will be that much higher because this we are finding the del T, right? So I am adding here 2.17, so it will be in Kelvin. So what we will get? 272 Kelvin, right? So now moving to the options. So that is option A. Got it? Okay. So which of the following statements is correct to the first and the second order phase transitions? So today also I just give you a brief description about first order and the second order phase transitions. So let me know what is the answer. So for the first order phase transition, your chemical potential is continuous function at temperature, and the first derivative is discontinuous. Your first derivative is, so your first chemical potential conscious, no. Your first derivative is continuous, no, right? So your first part is wrong. For your second order transition, your first derivative is continuous while your second derivative is discontinuous. Your first derivative is continuous, right? So that will be option D, right? Okay. Moving to next question. What fraction of enthalpy of vaporization of ethanol 1 mole is spent on expanding the water vapor assuming idle behavior? So your del H vapor is 43.5 kilojoule per mole. So you have to find the friction, that is so I am using the equation del H equals to del U plus P plus delta V PV. So from here you know your del vapor H is equals to 43.5 kilojoule per mole, and your del vapor PV is equals to so I am keeping the pressure constant and changing your volume. So that is your gas minus your liquid. So from here we know your volume of gas is higher than your volume of liquid. So I am assuming V liquid equals to 0. So that is PV gas. So this PV equals to nRT. So we know. So here I am considering your number of moles are 1 for perfect gas. Okay. Next we are doing what we are doing. Del vapor PV is equals to your RT. So your R is 8.314 joule per Kelvin per mole into your temperature. So here temperature is So what is the boiling point of ethanol? It is around 78 or 79, right? So we are considering your temperature equals to 79 degrees Celsius. Okay, and converting into your Kelvin. So what will be in Kelvin? How much? 352, right? So now I am putting 352 here. 352 Kelvin. So now what you will get after multiplication? How much value? You just need to multiply 352 into 8 into 8.314. You will get 2927 joule per mole. This is what you are getting. Okay, Gopika. Okay. So ultimately you have to find the friction. Okay, this is fraction, right? So what fraction of your enthalpy of vaporization of ethanol is spent on expanding the water vapor? So your fraction will be your delta vapor PV upon del vapor H. So this is our initial value, right? So here we are expanding your equation to in terms of your pressure and volume, right? Pressure and volume here. So but this is your initial value, so you have to find the fraction between your final and your initial. So your final is this one that we are calculated, that is 2. So I'm converting into your kilojoule, 2.927 kilojoule per mole. 2.927 upon your del vapor H is 43.5 kilojoule. 43.5 kilojoule per mole. Kilojoule per mole, right? So what you will get? What is the fraction? So what is the fraction? Okay, you both are getting same. It's correct, 0.067, right? So now going back to the option, 0.067, option A. So your answer is option A. Okay. So next question is, the specific volume of monoclinic sulfur which is stable above the transition temperature is greater than that of the rhombic sulfur by 0.056 centimeter cube per gram. The transition point at 1 atmosphere pressure is 350 Kelvin and it increases at the rate of 0.035 Kelvin per atmosphere. Calculate the molar and enthalpy of transition. So here your given molar mass of sulfur is 32 gram per mole. So here ultimately you have to find your molar enthalpy of transition. That means you have to find your transition, del transition H, molar enthalpy, right? So this is what you have to find. So here given is the transition point at 1 atmosphere is, that means 1 atmosphere pressure, your temperature is 350 Kelvin, right? And your volume, what it's saying, your specific volume of monoclinic is table of the transition temperature is greater than your means your del V, del transition volume, that is Vm monoclinic minus Vm rhombic is given. So that means your change is given is 0.056 centimeter cube per gram. Okay. So this is your molar volume, but now I am multiplying with your 32 molar weight, that is 32 gram per mole, right? So this gram will cancel and you will get, so what value you will get? 0.056 into 32, what will it will be? Yeah, it's 1.792796 into 10 to the power. Now I am converting this centimeter cube into decameter, so that will be in 10 to the power minus 3 decimeter per mole. So next, what we are trying to find, so del P upon del T, but here I am considering your del T upon del P. So here your 0.305 increases. So here your transition point at 1 pressure, and it increases to the rate of this. So this is Kelvin upon, sorry, so this is okay. So this is your Kelvin, means temperature upon pressure, right? So here I'm writing here dt upon dp is equals to how much? 0.3035 Kelvin per atmosphere. So from here I can define dp upon dt is equals to, so what will be the reciprocal of this? Just do 1 upon 0.035, what you will get? Okay, it is 28.57. So now it will be atmosphere per Kelvin. Okay, so now you know this Clapeyron equation. So I'm using this equation. So this is dp upon dt is equals to del transition h upon T temperature into transition your Vm. Okay, so let me write into the clear form. So this will be T transition Vm. Okay, so now I'm keeping this to the left hand side, del transition A, this term, and other thing to the right hand side. Okay, so this is your temperature into del trans volume, right, into your dP upon dt. So now your temperature is 350, right? This 350 I am writing here, 350 Kelvin into your V transition. This transition we got is 1.792. How much? 1.792 into 10 to the power 3. So I have converted into decimeter cube per mole, and dP upon dt. So dP upon dt we have just calculated here, this one, that is 28 into 28.57 atmosphere per Kelvin. Okay, so what you will get after multiplication? This will be around, I think, 17919 point. Okay, ten to the power minus 3 dm cube per mole atmosphere. So I am keeping here, that will be your answer that you are given, 19. So there is no need to write this much, right? Sorry. So now converting your atmosphere into your kilopascal. So it will be your 101.325 kilopascal. Okay. So I am directly multiplying and writing your answer, 1815.65 joule per mole. So after calculation and after converting your units, you will get joule per mole. So this will be option A, 1815.65 joule per mole. That is option A. Okay. Next question is, calculate the melting point of ice under the pressure of 100 bar Assume that the density of ice under these conditions is approximately 0.92 gram per centimeter cube and that of liquid water is 1 gram per centimeter cube. So here you're given enthalpy of fusion is there will be some value, I will check. Okay, so your molar mass is 18. So your enthalpy of fusion is, let me check, yeah, so yeah, delta HF is, this is given, okay, this value is missing, so I'm just writing here 6.01 kilojoule per mole. So this is your given. So calculate the melting point of ice. You have to find the temperature under the pressure of 100 bar. Assume the density of ice under these conditions is approximately 0.92 gram. So density is given 0.92 gram per centimeter cube and that of liquid water is, so you are having a varying densities, solid and liquid. This is your ice and this is your liquid. This is now 1.0 gram per centimeter cube. Okay, so now we can find the change in temperature. So your change in temperature will be TF final, that is at 100 bar, minus TF minus at 1 bar. Okay, and before we just have calculated the value in terms of your density, right? So what was the value, equation? So I'm directly taking from there. Okay, let me write down the direct equation. So you know the equation that we have formulated just in previous questions, that is TF into change in pressure into mass upon fusion delta fusion H into change in your density. Right, this equation, I'm talking about this equation we have derived just before, right? So I'm just putting these values here. So our TF is so this temperature I'm considering at 0 Kelvin. From that is the temperature where your solid and liquid is changing, right, at equilibria. 15 Kelvin into your change in pressure del P, $100 bar, and your initial 100 bar So I'm converting into your Pascal into 10 to the power 5, right? Minus your 1 bar, your normal 1 atmosphere, like 1 bar that I'm considering here, into your how much, 18 gram is given, right? 18 gram of water, 18 gram your molecular weight, into I'm converting into kg, so that will be 10 to the power 3 upon mole, right? So your del fusion is 6.01 into 10 to the power 3 joule per mole. Okay, and your change in density is how much? This liquid minus ice, 1 into 10 to the power 3 kg meter cube minus 1 upon how much? 0.92. Okay, 0.92 into 10 to the power 3 kg per meter cube. Okay, so after solving this whole, you will get del T is equals to how much? How much you will get? Okay, let me write down the del T is minus 0.707 Kelvin. Okay, so now one thing I forgot to mention here, I'm converting your this bar into your Pascal, so it will be your 99 into 10 to the power 5 Pascal. Okay, so instead of bar I am considering your Pascal. 1 bar equals to 10 to the power 5 Pascal, so that's what. Okay, so I am converting the unit here. Okay, so this is your del T. So your TF is at 100 bar is how much? So this is your change in temperature. So now you have to add that temperature that we have just calculated. So that is 273.15 Kelvin plus minus 0.707 Kelvin. So this will be how much? 272.443 Kelvin. Now checking the options, 272.84, right? This 272.44, yeah, it's 44. Okay, sorry, your decimal is changing, not your sorry, that is your 572. Okay, this is 272, right? So this is your 272.443, that is option D, right? Okay, let's solve one question, this 10th one, and we will solve this 9th question in next session. Okay, So I'm solving your 10th question here, your last one. So it says the temperature dependence of vapor pressure of solid X can be approximately represented by the relation. This is a similar case that we have just solved, right? Your pressure was in torr equals to 10 minus 1871. I think this is the easy one. You people can also do this, right? We have just solved the similar type. And your log to that of liquid. Eight minus 1425. Now estimate the temperature, this temperature and pressure of triple point, this P3 and T3 of X. Okay, so now you have to find your triple point, that is T3 and P3. So we know at triple point your T3, the vapor pressure of liquid and your solid are equal. So therefore now I'm equating these two equations. Okay, I'm writing down here. I'm equating your right hand side of both the equations, that is 10 minus how much, 1871, and I'm keeping your T as T3. Okay, T3, and your T3 per T per Kelvin will be Kelvin here, is equals to how much, 8 minus 1425 upon T3 K. So similarly here also I'm keeping your T3 here and Kelvin above, because T upon K, right? So now your both T3 is same. Take the T3 terms in one side, minus 187 upon T3 plus 1425 upon T3. So this is whole Kelvin is equals to 8 minus 10. So this will be minus 2. Now solving this T3, how much you will get? How much you are getting this T3? How much is the value of your T3? Okay, Gopika, it's 223. Right, it's 223 Kelvin. So you will keep the Kelvin to the, take the Kelvin to the right hand side, and again you will get your, this is how you will get your T3. So now you have to take your find your P3. So now you're having your T, only one variable you left, that you have to find, that is P. So now use any of the equation to find your P3, because both the equations will be same at your triple point, right? So I am using your log P3 is equals to this equation, minus 10 minus 1871 this is your K Kelvin upon 223, your temperature value that you got. Okay, now what you will get after this? So what will be the value of this? 10 minus 1 upon 1871 upon 223. Okay, it's 1.61. Okay, it's 1.61. Okay, so now this is your log. Now take the log another side. What you will get? Take the antilog of your 1.61. What will be the value? Okay, this is 40.71. Okay, so this P3 is in your torr. See the equation again. So this is your pressure per torr. Okay, so again I am putting torr here. Okay, now P3 is equals to 40.71 by taking your unit to other side. So this is your P3, right? So now checking the options. Your temperature is 223. Okay, this one, and your pressure is 40.47 torr. Correct? Okay, so your option is option B. Okay, so last question we left, we will do in the next session. Okay, so do you have any questions regarding to today's class? Okay, otherwise thank you, and thank you for your kind patience and attending this class, and we will meet you at the same timing 6 to 8 in the next week for the week 7 assignment questions. Okay, thank you all.